All right, let's talk about something that sounds like it's straight out of science fiction, but is getting more real every single day: quantum computing. We're going to dive into a totally new kind of machine, one that operates by the bizarre and, frankly, super powerful rules of the quantum world. Okay, so what's the big deal? Well, it all boils down to one fundamental, kind of mind-bending difference. Your laptop, your phone, they all use bits. Think of them like a light switch. They're either on or off, a 1 or a 0. Simple. But a quantum computer uses a qubit, and the best way to think of a qubit is like a spinning coin. While it's spinning, is it heads or tails? Well, it's kind of both at the same time. And that one little trick is what unlocks almost unimaginable computing power. So here's how we're going to break this all down. First, we'll get into what makes this such a huge leap forward. Then, we'll look at the insane challenge of actually building one of these things. After that, we'll meet the quantum gremlins, the big problem standing in the way. Then, we'll explore the incredible new era of power this technology could unleash. And finally, we'll look at the global race to get there first. Okay, let's dive into that quantum leap. We're basically leaving behind the world of computing that we know, the predictable one, and stepping into a whole new realm where the rules of the game are just completely different. So, the first new rule has a fancy name: superposition. It's really just the sciencey term for our spinning coin. Because a qubit can be a 0 and a 1 at the exact same time, a quantum computer can explore a staggering number of possibilities all at once. It's not checking pads one by one like a regular computer. It's like it's checking millions of them simultaneously. And this changes the whole game when it comes to problem solving. A classical computer is deterministic. You ask it, what's 2 plus 2? It follows a straight line and gives you 4 every time. A quantum computer, though, is probabilistic. It explores all the possibilities and tells you the most likely answer. It's not about finding one certain answer. It's about navigating an insane amount of complexity to find the best possible solution.
Okay, so if the theory is so amazing, how on earth do you actually build one of these things? I mean, trying to harness this quantum weirdness is one of the biggest engineering challenges humanity has ever taken on. It's one thing to talk about spinning coins, but it's another thing to build a machine that runs on them.
And yeah, that is not an exaggeration in the slightest. The source material is crystal clear on this. Building quantum hardware is a truly monumental task. The level of precision, the amount of control you need, it's unlike anything we've ever had to do before. You know, what's really interesting is that it's not like there's one single blueprint for a qubit. It's more like a race between a few different approaches, and each one has its own pros and cons. You've got superconducting circuits, which are super fast, but you have to keep them colder than deep space. Then there are trapped ions, which are really stable, but making a lot of them is tough. And then you have photonic qubits, which use light itself, but they're easy to lose. It's a huge scientific bake-off, really. Which brings us right to our next big topic, the so-called quantum gremlins. These are the fundamental make-or-break problems that scientists are battling every single day as they try to turn these impossible machines into a reality. So, you gotta ask, right? If this stuff is so powerful, so game-changing, why don't we have quantum laptops yet? What is it that makes this so unbelievably difficult? Well, the answer really comes down to these 5 massive hurdles. The biggest one is that qubits are just incredibly fragile. The tiniest vibration, the slightest change in temperature, what scientists just call noise, can completely mess up their delicate quantum state. This collapse is called decoherence, and it creates errors that are a nightmare to fix, which makes scaling up to thousands or millions of qubits so hard. And of all these problems, decoherence, man, that's the big one. It's the true arch nemesis of quantum computing. This is the moment our spinning coin gets bumped by the outside world and just collapses into being plain old heads or tails. The quantum magic is gone, poof, and all that information it was processing is just lost forever. So the main battle right now is just protecting these qubits from decoherence. Okay, but let's imagine for a second. What if we do win that battle? What if we can tame those gremlins? If we can, we unlock a completely new era of computing power. So let's look at the amazing things we could do with it, and the really profound risks that come along for the ride. And believe me, there is a ton of money riding on this. The market for quantum computing is projected to rocket to $125 billion by 2030. Now, that's not just some random number. It's a huge global bet that this tech is going to solve problems that are literally impossible for even the most powerful supercomputers we have today. But with all that incredible power comes an absolutely enormous risk. Probably the single biggest threat is a quantum computer's ability to break nearly all of the encryption that protects our digital lives. We're talking everything from your bank account and private emails to top secret government data. The threat is so serious that some people have started calling it the encryption apocalypse. So here's the scary part. Here's how it would actually work. Right now, most of our sensitive data is protected by a kind of classical lock. It's basically a math problem that's so hard a normal computer would need thousands of years to crack it. But there's a famous quantum recipe called Shor's algorithm that can pick that lock like it's nothing. And just like that, everything we thought was safe is suddenly wide open.
Okay, so for all that doom and gloom about encryption, the flip side, the promise, is just as huge, if not bigger. A quantum computer could simulate molecules with perfect accuracy, helping us discover new life-saving drugs in record time. It could help us invent revolutionary materials, build way more accurate models of the financial markets, totally optimize global logistics to save fuel and time, and just supercharge the development of AI. The possibilities are huge.
All right, this brings us to our final leg of the journey, the global high-stakes race to build this quantum future. Who's actually building these machines? And, how close are we, really? And hey, don't just take my word for it. Just look at the roadmaps from the big players. This is not science fiction anymore. Companies like IBM, Google, and IonQ all have public plans showing an incredibly aggressive push to scale these machines up. We're seeing the number of qubits just grow and grow year after year, going from hundreds today to potentially thousands in the very near future. The progress is real. And you better believe this isn't just a bunch of companies competing. Nope, this is a full-on global race. Countries are pouring billions and billions of dollars into their quantum programs. China, the EU, the United States, they're all making these huge strategic bets because they know that whoever builds the first truly powerful, error-corrected quantum computer could gain a massive advantage, both economically and strategically. So all of this, it leaves us with one massive, lingering question. As this technology comes online, we are going to have a tool with power we've never seen before. A tool that could cure diseases or it could break global security. The question isn't just if we can build it anymore. It's once we have it, what problems are we as a society going to choose to solve first?